All right. A quick announcement. Your homework assignment has been set up on Carmen. Okay, it's a PDF file. You can find it under assignments or you can find it under homework on the modules. I made a small change to the homework assignment. Problem C has been made into an optional problem. Okay, this is because I may not have the time to get to that material today. So I'll probably get to it on Wednesday for sure. Not probably, for sure. If you want to solve it after Wednesday's lecture, that's fine, but it's optional. You don't get any extra credit for it. You gain my respect, that's okay. All right. So we're going to start off today by doing something slightly different from what we've been seeing before. We're going to look at vertical systems. Okay, so the simplest example of a vertical system is just a spring and a mass connected to each other. Okay, so I have a spring, I have a mass, I connect them together. I apply a force F of t. And my aim in this problem, this very simple, silly problem, is to actually find out the equation of motion. Okay? So what is the equation of motion? We proceed through in the standard manner. You set up the XYZ coordinate frame. I put some restraints on the particle. And next week we will start rigid bodies. So they are slightly fancier cousins of the particles. Okay? So I have my XYZ system. And I set up the number of degrees of freedom. Okay, I find out that there are no rigid bodies, so R is 0. Number of particles is 1. The number of constraints, the total number of constraints on each particle is 2, because in this case the particle cannot travel along the horizontal direction. The particle cannot travel out of the page. Okay, so in this case C is 2. So the number of degrees of freedom, 6R EP minus C is going to end up being 1. We know this because we've solved multiple problems of this kind, but horizontal. Okay, so in this case we can decide that the displacement of the particle is a degree of freedom. And so I'm going to call it as y of t. So say y of t is the degree of freedom. This is the displacement of the mass. So far so good, no surprises. Okay, really. The biggest challenge in vertical systems is to decide where the static equilibrium position is. And I always follow the procedure that I'm going to show you. Unless otherwise I tell you to do something else, I expect you to follow the same procedure. Okay? So the idea is, where is the SEP? And why is this a challenge is because even if I don't apply a force on that particle, even if I don't apply that force F of t, you see that the particle has a certain weight, and because of this weight it is going to displace vertically down no matter what I do. And so I have to account for that particular displacement of the mass, which will stretch the spring statically. Here is how I approach it. I'm going to do this only for today. From next time onwards, I'm not going to spend too much time describing how this is done. Okay? So let me do the following. Figure 1. Only the spring. The spring, we assume it to be massless, so the spring does not have any inertia associated with it. So if I let the spring be as it is, it's going to lead a very gentle and peaceful life in its unstretched length. I come and I take this particle of mass m and I attach it to the bottom of the spring. But that's all I do. I do not apply any force F of t. Okay? So in the next location, I come and I gently, it's almost like this if you have seen a spring balance, right? You're trying to lift something by using the spring balance, by hooking the mass to the hook of the spring balance. The spring balance, you don't want it to oscillate crazily because that's dangerous for you. So you gently come and you place the mass moves down, the spring gets deflected, you have your analog reading on the scale. That's exactly what's going on here. I come and I apply the mass to the bottom of the spring, pulls it down. But you see, no applied force. So what happens is that after the mass is attached to the spring is deflected statically and it comes to rest. Okay, so this I call as the static deflection of the spring. Delta static. And now the system is in static equilibrium. Okay, so this is now static equilibrium. This is the static equilibrium position. I'm going to draw the free body diagram of the spring and the mass now. Okay. Spring. The mass. Please let me know if you cannot see my writing clearly, people in the back. For a positive static displacement, it makes common sense, right, that if delta static is pointing down, the spring is getting stretched. Okay. So I'm going to say that for delta static pointing down, the spring is stretched by F spring static, F suffix S static. ST stands for static deflection. The S within the brackets stands for the spring. On the mass, there's an equal and opposite force, F static. I should have drawn it a little to the left here. Let me do that. So this is also Fs static. Importantly, there is the mass times the acceleration of the block because the mass has a certain weight associated with it. It does not have any geometry. So at the static equilibrium position or at SCP, the mass does not have a kinetic diagram because it does not have any acceleration. It is just coming, catching hold of the spring and gently coming to rest. That's all it's doing. So I just have to use statics here, which means sum of all the forces is equal to 0. Okay? So in this case I say that at SCP, sum of all the forces is equal to 0. Forces pointing down are positive or pointing up are positive. Does not matter really. And by common sense, this tells me that mg is equal to F spring static. What is F spring static? It is nothing but the stiffness of the spring times the net static deflection of the spring, which is going to be delta static. Okay, one end of the spring is attached to the wall. It does not undergo any displacement. The other end of the spring is getting stretched. So what's the net displacement? Delta static at the static equilibrium position. So this is just K times delta static. Then I come and say, okay, this is not what I want. I want to do something more complicated than statics. I've taken it in my senior, whatever, sophomore, or so maybe I took it in my senior year. That's why I'm here. But I want to do something complicated. Okay, I want to do dynamics, right? So I take this guy and I apply a force on that person. Which means that I'm taking that and displacing it from the static equilibrium position, but in a time varying manner. This is just going to keep oscillating up and down. And we come back to a regular system with the displacement applied from the static equilibrium position. This is the important statement. I bring it to the SEP, and then I apply my displacement from the SEP, which is y of t. I choose a positive sign convention. This is plus y dot, y double dot, and so on. This is my sign convention from SEP. Then I draw the figure. With the force F of t applied to the mass, and so the displacement of the mass from the SEP is y of t. Okay, so I want to write it here. Y of t is displacement measured from SEP, which makes it an absolute quantity. Okay, this is the reason why we want to decide where the SEP is, or decide where the SEP is. Once I do this, then I'm going to draw the free body diagram of the spring and the mass and the kinetic diagram of the mass. And here is where you're going to be careful. So after displacement, I have the spring, I have the mass, the kinetic diagram, and the free body diagram. The easiest thing to draw in all of these things is the kinetic diagram, because it's mass times acceleration. So that's the first thing I'm going to mark here. Okay, so this is m times y double dot. Why am I drawing it in this direction? Is because this is the direction of my positive acceleration, y double dot. Okay? Can somebody help me with this spring free body diagram? What are the forces? And let's assume that y of t is positive. So for y of t greater than 0, spring is in tension. This tells me that the mass is not moving down. That's not what it tells me. It tells me that if the mass were moving down, then y of t is going to be a positive value because of my sign convention. Invisible presence there. All right, can somebody tell me what are the forces on the spring? Yes, go for it, first hand.
Is it the spring force, which will be K times y of t plus delta static?
Fantastic. In this figure, I not only have to include the spring force due to the deflection y of t, but you notice that the spring was previously deflected by an amount delta static. So you have to add that as well. Okay, so in this case, what I typically do is I say the following. It's in tension. Fs static, which was remnants of its previous behavior, plus Fs, which is the spring force once I start applying the displacement on the mass. Okay, likewise, I'm going to have Fs static plus Fs. This point on the spring, once again I want to make this point very, very clear. This point on the spring is connected to the top point on the mass, which means that the forces there will be equal and opposite. And so I have the force on the mass as Fs static plus Fs. What are the other forces on the mass? Anybody else? Yes? Absolutely, I need that. That was my question. What are the other forces on the mass? Fantastic. And then obviously the applied force F of t. Okay, that has to be included. So this is the free body diagram. This is the kinetic diagram. Is this clear to everybody? I start off with no mass. I gently come and attach the mass, so the spring is deflected statically. Then I take the mass and I apply the time varying force F of t so that its actual motion starts. But as I do so, I have to ensure that I accounted for the previous incarnation of its life, which was its static behavior, which is all included in the form of Fs static and mass times weight, gravitational acceleration, okay, which is the weight of the body. Now, sum of forces in a free body diagram and kinetic diagram. sign convention is followed. On the free body diagram, mass times acceleration due to gravity, mg, then f of t minus fs static minus fs. These are all the forces, external forces and gravitational force. In previous problems, we did not include the gravitational force because the motion was not in the direction of gravity. It was in a horizontal direction. So whatever gravitational force was balanced by the normal reaction to the ground. That's not the case here. And if I were to be really true to it, I will have normal reactions on the walls as well, but some N1 and N2, and they should obviously be equal to each other. Okay, we are not worried about it, just forget that. Worry only about the direction of motion. Once I do this, this is m times y double dot. But do you see what I see? Do you see something juicy? Yes?
mg minus f static is 0.
Fantastic. mg and f static cancel each other. Okay, so magically, these creatures which are just there to make your life miserable, they vanish. And if I then substitute and bring it to the natural form or the actual form of the ODE, and hang on a minute, I'll answer your question. I get my double dot plus ky is equal to f of t. The great thing is the following. If I start the problem from SCP, and if I know that the spring is deflected statically by the mass, then I do not need to include the static deflection of the spring, nor do I need to include the weight of the body. And in many situations, why is this advantageous to us is because in many situations, if I do not start from ACP, then this weight mg will be a part of the right hand side of the ODE, which will make it a non-homogeneous system, which just completely messes with my mind. I don't like it. Nobody in dynamics likes it. But there are very tricky problems where even if you start from SCP, you cannot get rid of the weight of the body. And this is inherently true in a problem we're going to solve next class. I want you to think about it. This problem is a beast. This is an example of a springy pendulum, like a yo-yo. I take a yo-yo, it can go radially, it can also rotate. So it not only has radial motion, but it also has rotary motion, which means that this simple little thing is a 2 degree of freedom system. And the problem is, even though the spring is statically deflected by the weight of the ball, it is the force of gravity that restores the rotational motion back to where it should try to be. Okay? We're going to derive this equation of motion in the next class, so hang on to it. So this is a system where this simplification does not work. So this is an outlier. And it is impossible to know what is an outlier and what is not, which is why I always advise this course of action. You start off with nothing. You come and you gently add the mass. The mass deflects the spring. You include every damn thing in the equations. And you let the physics do the talking, not your intuition. Don't trust yourselves, trust the physics. Okay, this is always true if you perform everything carefully and with deep consideration of the physics. All right, does this make sense to everybody? Now I'm going to take some questions. Somebody here had your hand raised. This is you.
So you want us to trust the physics, include everything, including our static equilibrium?
Absolutely. Unless I tell you not to do so. Which means you're trusting me, which is obviously with a pinch of salt. Okay? All right. You can't trust me. I'm going to take a more complicated problem. And let's see what happens if I bring in a damping element. Does it dampen our enthusiasm? Let's see. also known for my very poor jokes. So if you do laugh, I'll give you some extra points. All right. So for the next 35 minutes, I'm going to go on a very intense problem, right? This problem is an example of what is called as a tuned absorber. So this is a 2-degree of freedom system with two masses connected in the following manner. I have one mass, then I have a little more space. All right, so I have two masses here, masses M1 and M2. I have three springs here. Stiffness is K1, K2, and K3. So this is K1, this is K2, this is K3, and then I have a damping element of damping constant C. Okay? I need to obtain the equation of motion for this system. And as I said, this is a tuned absorber, which means that this small mass M1, which is drawn small, is capable of reducing the oscillations of the mass M2. And we're going to study this in greater detail, including the solution and the physics behind it, as we come across this maybe in about a couple of weeks' time. I'm going to follow the same thought process as we did for the previous problem. Okay? So first things first, coordinate system and so on. And it is understood, okay, I'm not going to draw the restraints on the sides. It is understood. Do you guys have a question? Okay. It is understood that there is no motion in the horizontal direction. And it is also understood that there is no motion in the out of the page direction. Okay? So we're going to keep that something as fixed in our mind. I'm not going to draw these guides. All right. Number of degrees of freedom. Six times 0 because there are no rigid bodies. There are two particles here, so 3 times 2. How many constraints? I have 2 constraints for each particle, which means that I have 4 constraints in total. Okay? So this is minus 2 times 2. What are the constraints for each particle? They cannot travel horizontally and they cannot travel out of the page or into the page. Okay, those are the constraints. So the number of degrees of freedom is equal to 2. And as you may have guessed, the displacement of the masses will be the respective degrees of freedom. Let's call them as y1 of t and y2 of t. So say degrees of freedom, these are the displacement of M1 and M2 respectively. Okay? Here's my stick. From next lecture, I am not going to go over this particular step unless otherwise we are solving a very challenging problem. For things like this, we will just figure out and say this is 2 degrees of freedom. I'm not going to waste my time. All right. Same strategy as before. I draw the entire thing without the masses. I come and I gently attach the masses, let it deflect statically, and then I apply the different forces. Let's say I apply a force on this mass, F of t, just on that mass. Okay. So first step, without anything. This is the setup. And of course, this thing is not going to live in free air. It is just a caricature of the problem. Okay? Yes, yes.
Why do you flip the orientation of the damping element on your
Oh, it does not really matter because it is just a piston and a cylinder. So it does not matter which way the piston and the cylinder is. All we care about is what is the velocity at the ends of the dampers. But that's a good observation. Okay? I like that. All right. Now I come and I attach the masses. I let the whole thing deflect statically. Make some space for myself. All right. Apply one of the masses first. The other one. This is the situation. Now don't be fooled by the exaggerated nature of the figure. These blocks are all treated as particles. They do not have any geometry associated with them. Okay, so if things seem a little askew, just go with the flow. So what do I see first? I see first that this spring is going to be statically deflected by the mass, which is of magnitude m1. Okay, so if I look at that, I'm going to call this as delta static 1. Okay? Then I'm going to see that this spring and the other spring in the bottom, they are deflected by the same amount because they are attached to the same mass. So I'm going to call it as delta static 2. Okay? This amount here, delta static 2. Delta static 2. Does my figure make sense to everybody? Maybe I can increase the height of this to show it a little better. This is also delta static 2. Its stiffness is K1, K2, and K3. So this is K1, K2, K3. The damping element C. Why did I not draw any static deflection on the damping element? Okay, let me go to a different person. Well, you haven't answered the question yet. Okay, go for it. Go for it.
I have first a question.
Oh, okay, okay, go for it.
And then I can help with that.
Okay, sure.
Delta static 2 is just the static displacement from the weights of M1 and M2, or M1. Or M2
You see,
actually.
it is just M1 because M1, it is just M2 because M2 is connected to here, M2 is connected to here. All I'm looking at is the motion of only M2. So all of these delta statics that I'm talking about, this is the deflection of the mass. The deflection of the spring depends on where it is connected to the mass. Is it connected to one mass or is it connected to two masses? If it is connected to two masses, the spring can undergo a compression at the top and an extension in the bottom. Okay? And I'll have an example of that nature in my lecture notes. So my question, next question, which I'll throw it out as a general question. Why did I not mark any static deflection for the damping element? Even though it looks as if it's moved a little bit, which you are going to ignore in a while. Yes, go for it.
Oh, it's because the damping element is two pieces that like interlock within each other. So if there's deflection, the damping element from the outside perspective is still the exact same because it allows internal deflection.
Let's say that I have a what is called as a squeeze film damping element, which is a combination of a couple of bearings, okay, which just squeeze the film in between them to provide some viscous action. So that kind of an interlocking doesn't take place in such a bearing element, in such a damping element, even though the behavior is the same. So that's a good attempt. Any other answer? Yes, yes, yes.
It's because the force it applies isn't dependent on the distance that it's displaced.
The forces are not dependent on the distance it is displaced. I'm going to come back to you. You had your hand raised.
I was going to say that it's related to velocity and mass.
That is exactly the clarification of what you mentioned, and I think you must have been thinking about the same thing. A damping element does not react to displacements. A damping element reacts only to velocities. So even though the mass is statically deflected, the damping element cannot resist static deflection of the mass. That is why you have this spring fellow sitting here. If you see a problem of the following nature, somebody in the industry comes and shows you something like this, what is your reaction? They have not taken 3260 because this thing is absolute garbage. Because a damping element, a viscous damping element, does not resist static loading. That thing is just going to fall apart on their head. Okay? A damping element always resists only velocity. And so inherently, the actual physical model of a damping element is a combination of a spring and the viscous element. So this combination together is the actual damping element that you see in your doors and so on, the telescopic dampers that you see with the piston inside, fluid present inside. That entire thing has a certain stiffness. The stiffness is modeled by the spring, and it also has the capability to withstand or react against velocity, which is modeled by the presence of the damping element. So you cannot have something like this, but you can have something like the former. Okay? So this is something to keep in mind. I might wantonly give problems like this in the exam and ask you to find the equation of motion. And believe me, many people have diligently followed all the sign conventions and given me an equation of motion, which is absolutely wrong. Okay? It cannot be that way. You cannot have a system like that. A damping element cannot withstand lateral static loading. All right. So now I have this situation here. So this is at ACP. Okay, let's see what happens. I'm going to clear this panel here. This has done its part. Let's write out all the equations. So at ACP, so this is the SEP position of the entire system. For delta static greater than 1, static 1 greater than 0, I'm sorry, delta static 1 greater than 0, spring of stiffness K1 is in tension. But because delta static 1 dot is 0, this means that the damping element does not exert any restoring force to the static deflection. And point of importance, please look at my lecture notes from today's lecture after class. You have a 3-day weekend. Hopefully tomorrow goes well for all of us, right? And I'm hoping, expectant. After that, you can look at my notes. You will see some extra examples. Okay? After that, or maybe a couple of days after the after effects of tomorrow, you can take a look at my notes, either this way or that way. Okay. But I have some extra examples there, things similar to it, and maybe slightly on a different level as well. All right? So that's the situation here. Delta static 2, spring of stiffness K2 in tension. Watch out, K3 is in compression. With this done, let's derive the equations in static equilibrium. Okay, so at SCP, I'm going to draw the free body diagrams and so on. First spring is in tension, so this is Fs1 static. Likewise, the same magnitude there as well. The damping element, Fd static, is 0. So strike that off, you don't even need to draw it. If you see a damper, don't need to draw it in static deflection, okay, for the reasons that we've just discussed. Then the other two springs, one is in tension, the other is in compression, so let me draw it likewise. This is in tension, Fs2 static. And the third one. Fs3 static. Fs3 static. Okay? This is for delta static 1 greater than 0, delta static 2 greater than 0, and common sense tells me that these are all okay. I draw the free body diagram of the masses. Mass M1, excuse me, mass M2. Weight of the masses, so I'm going to have M1G, M2G, this is all at static equilibrium position. Then mass M1 is connected to the spring right here. The damping element right there, the damping element does not have any force in it, so I just have the force from Fs1 static. Does this make sense to everybody? Mass M1 does not have any other force acting on it. Okay? Mass M2 has two forces acting on it. One is this mass is connected to the spring of stiffness K2 right there, which means that there is an equal and opposite force. Fs2 static. What's the direction of Fs3 static on mass M2? Anybody? It has to be pointing up, right? Equal and opposite. Alright, so now we say, okay, at static equilibrium, sum of all the forces in the free body diagram is 0. For the mass M1, this is all at static equilibrium. Okay, so for mass M1, M1G is equal to Fs1 static, which is K1 stiffness times the static deflection. Then for mass M2, same story. Force is pointing vertically down. M2G, and then all the other forces will be subtracted. So I bring them to the other side. So this is going to be Fs2 static, Fs3 static, or M2G. Because the static deflection of the spring S2 and S3 are the same, they are moving with the same delta static, this is going to end up being K1 plus K2 times delta static 2. Can somebody tell me what that implies. When do I add the stiffness of two springs? You've been to recitations, I hope. When they are in parallel, fantastic. So even though it doesn't look that the springs of stiffness K2 and K3 are in parallel, they're actually in parallel with each other. Why? Because if you've been to recitations, you'll know that springs that are in parallel have the same displacement. Springs that are in series have the same force acting on them. So now in my problem, what I'm going to do is this. I'm going to say, okay, I'm not going to worry about K2 and K3 as separate entities. I'm just going to combine them together into one spring of stiffness K2 plus K3. Okay? So this is now going to be a set of springs in series. This is K2 and K3, I'm sorry. This is not K1 and K2. Apologies for that. This is K2 and K3. So I'm not going to look at both of them together. I'll just look at them as one lumped unit. And we're almost there. And so what we will do next is we are going to come add on to this figure by saying, okay, there is a force F of t acting on a mass m2. Draw it as a displaced entity now. Okay, so now I'm going to have, this is displaced by a certain amount. Sorry, this is the other way. I always get confused with that. Okay, now you see that I don't have two springs. I have added those springs up together. They are in parallel. They have the same displacements. Their net stiffness is the sum of these two stiffnesses together. So this is now K1. This is C. This is mass M1. This is C. K2 plus K3. Displacement of mass M1 is Y1 double dot, Y1 dot, and so on. So this is Y1. This is the direction of positive Y2. So these are my sign conventions. And now we are ready to draw the free body diagram and the kinetic diagram of the masses and the springs and the dampers and everything else. Okay? We got to be careful. The damping element is especially the tricky one here. Even though it did not have any static deflection, it's going to dynamically try to resist the motion of the masses by applying a restoring force. Please notice, for a positive velocity y1 dot, a positive velocity y2 dot, if the magnitude of y2 is greater than y1, what happens to the damping element? It is going to get stretched. Okay, and so this is the statement that we're going to write next. So for y1 of t greater than 0, spring K1 in tension. For y2 of t greater than 0, spring K2 plus K3 in tension, which makes absolute sense. Okay, and this is by a parallel set of springs. Same holds true for damping elements. You can have them in parallel as well. If you see them in parallel, just add the damping constants together. If you see them in series, you have the reciprocal rule, as you've been through in recitations. In recitations, they taught you the springs. Same idea for dampers. Okay, and for y1 dot greater than 0, y2 dot greater than 0, y2 dot greater than y1 dot, the damping element is going to get stretched. Okay, so damper gets stretched. With all this, I don't have enough space to draw the free body and the kinetic diagrams. I'm going to pull the other panel down. Okay, so let's do that first. And with your permission, I'm going to be a little lazy. I'm going to draw on these figures themselves. Okay, I'm going to erase, start from scratch.